Hi everyone, welcome to the Multithreading in Java full course. So multithreading is considered one of the most complicated and hard to learn topics in Java, and the general notion is that multithreading is only required for the high performance applications. But in reality, multithreading is used in almost every application where the Java is used. Doesn't matter it's a small application or it's a large application, it's an enterprise or desktop application, so multithreading is used everywhere. So for example, let's take an example of, let's say the example of one of the most popular and one of the widely used frameworks in Java, Spring. So the Spring is, so when we are working with the Spring, so we don't actually deal much with the multithreading, but behind the scenes, multithreading is also used in the Spring application. So what's the Spring application? When we build a Spring application, when we build enterprise application in Spring Framework, so what we do usually, right? So we are deploying to one of the web servers. So we are either deploying to Apache Tomcat, the most popular, or we are deploying that to Jetty or similar frameworks. So what happens is that and usually we are building the REST endpoints, or in some cases we may build the GraphQL or gRPC, but mostly let's say we are building a REST endpoints for our enterprise Java application in Spring. So what happens is when we receive a request in the HTTP, that request first lands in our web server, right? Whatever web server we are using, that web server assigns a worker thread to that request, and then after that, that request goes to our framework. So to put that into the details, so whenever we are receiving a request, we are receiving HTTP request, and that HTTP request it's basically, so we are creating a socket connection, right? So under the hood, HTTP request is nothing else, just another socket connection. So we are receiving the HTTP request, and after that, so what happens? So after that, what happens is that the Tomcat captures that request, and Tomcat assigns to that worker thread. And after the worker thread is assigned, then after that, in that thread, so what we do, right? So we are going to the next level, which is the servlets, which is the Spring built on the top of the servlets, right? So what we do is, so we are going to the servlet level, and in the servlet level, we are capturing that request. So we are whatever config we have for the Spring security, so we are passing those filters, and then after that, that request goes to the dispatcher servlet, which is in turn handles that to the Spring MVC, handles at the Spring MVC, which captures the request, and through the controller and the service layer, it goes to the repository and returns the response. So in all this chain, right? In all this chain, so what happens is that from our perspective, right? If we are using the Spring Boot or let's say core Spring, we are just creating another controller, and we are creating service, and we are creating a repository and also DAO layer. So we are handling that request. But behind the scenes, that application is multi-threading by default. So multi-threading by default, why it's important? It's important because when you are working with these applications, you have to be mindful about the multi-threading. For example, one of the major issues that may be there when you are using a Spring, you may hit the race condition. So what it means is, let's say that you are using, in most of the cases, right, the type of the bean that we are using is a singleton bean, and in the singleton bean, if you are using a field that is shared among the threads, because we are creating only one copy of that singleton thread, right? So if you are using a field that is shared among the threads, then in that case you may have a race condition, or we may have another issue such as the deadlocks or the thread exhaustion and the similar. So that's the first part. That's the first part why it's important to learn the multi-threading, even in context of the web application, right? Even in the context of the Spring. And the second part is that what is the Java thread actually is. So for example, in our case, when we create a Java thread, so what we do from our side, we are creating a new Java thread. But from the Java perspective, Java doesn't handle that thread. So what Java does is Java hands that over to the operating system thread, right, or to the native thread. So what happens here is that when we are creating a thread, that is one-to-one mapped to the operating system thread. That's why when we are creating a thread, we need to be mindful about how much underlying memory we have, how much underlying CPU, in the CPU, how many cores we have. So this is all important when we are creating our application. And also, let's say that we cannot create a limitless number of the threads, right? That's why we are creating a thread pool in order to not hit the condition such as that the sum of the threads doesn't get the time for the execution. So for that reason, we are creating a thread pool. So that has been the case until the Java 21. After Java 21, so what we have right now, Java JVM actually can handle the thread. So for that, so what we have is we have a virtual threads, and in the virtual thread, they are mapped within the JVM, they are mapped to the carrier thread. So they are mapped to the carrier thread, but the carrier thread, in return, it's mapped to the underlying operating system thread, native thread anyways. So it's a kind of improvement from the Java perspective, but again, we still have the same limitation that our threads, whatever, either we are creating a virtual thread, or let's say that the old way creating a thread, so that those threads are mapped to the operating system threads, and we need to be mindful about the operating system limitations such as the stack, memory, and the CPU, and how many cores we have. So in this course, I try to start from the very beginning, start from the very first step, and the step-by-step explain that what is the thread, how we are creating a thread, so what are the different ways of the creating thread in Java, and so on. So also in this course, what I try to do is I try to also include the theory into the code. So what it means is, if you, let's say you watched all these videos and after some time you may forget that, okay, or you may want to refresh your memory about the multi-threading. So if you will go back to these videos, or if you will open the code, you will see that the theory is the part of that code. So I just added them as a part of the comment in the Java code. So hope you will enjoy it. And if you will have any comments, if you will have any ways how to suggest to improve this course, then please leave your comment below. Please enjoy. To understand multi-threading in Java, let's take a look at this very simple example. In this example, what we have is we have a program hello world, and in the main method, we are creating a new user, object user, and we are printing that. So what's going to happen under the hood when we run this program? Under the hood, in the heap memory, user object will be created, and also since we are starting with the main method, one main thread will be created. So there is always one main thread that is created in Java to run the main method. But let's say that we are adding more to this logic, right? So we are also saving the user data, and also we are uploading these videos. We can all do that. We can do these two operations in the main thread, but what we do in our case is we are creating a separate thread for each one. So what happens is that the JVM creates a separate stack for each of these threads. So now we have three stacks, right? Main thread, first stack, the T1, which is the saving the user data, another stack, and the T0 that's saving the user data, and the T1 that uploading a video. So we have three threads in this case. So how it works under the hood? Under the hood, we have three threads is created by the JVM, and what JVM does is JVM handles that to the operating system scheduler to schedule those threads on the operating system. So under the hood, it works that we have three threads, and each thread is mapped to the operating system thread using the OS scheduler. So that's called the multithreading. So multithreading is basically we are separating one program to a separate thread, so separate unit of work. So in our case, creating and running the main method, which is that the creating user, and also it's a one thread. Saving the user data is another thread, and then the third thread, what we do is we are uploading the video. A process is an independent programming execution that has its own memory, its code, data, and the system resources. So for example, the perfect example would be a browser. Let's say we have a browser. Browser in itself is a process. So in a browser, what we have, right? So we are downloading a file, we are sending HTTP requests, we are loading JS files, and so on. So all of these are separate unit of work, downloading a file, and we can do them in parallel, right? So we can download the file at the same time we can send HTTP request and load the JS files. So all these units of works, they are called threads, and all these works are combined, so one process can have several threads, right? In our case, let's say that we have mentioned here only 3 threads for browser, but in reality, it has much more. So let's take another example. Let's take example of Java. Let's say that we have a Java file, and in the Java file, what we do is we have a main thread, and for 2 other methods, for the saving a user data and for uploading that, we are also creating a separate threads. So what is the process in this case? Well, in this case, the JVM itself is a process. If you look at whatever operating system you use, if you look at the processes, you will see that whenever you run a Java application, JVM is created, JVM process PID, which means that the process ID is created. There are 3 ways how we can create a thread in Java. The first one and the most simple way of creating a thread in Java is to extend the thread class. And for example, here we are creating a class myThread that extends a class thread, and we are overriding a run method. In the run method, we can put whatever logic we want. For example, in this case, we are printing here hello from thread, and also we are getting the current thread, whatever the thread is, and they're getting its name. So let's run it. Let's create in our main method, in our main thread, right? We are creating another thread using a thread class. Let's run it and see the result. So as you can see here, hello from thread, and the name of the thread is thread 0. So now let's go to another way. Another way is creating a thread in Java is to use a runnable interface. So what we do is here we are creating a class myRunnable which implements the runnable interface. And the runnable interface, again, we have a run method in the we can put whatever logic we want in the run method. Here we just simply printing hello from runnable, and we are plus the name of that thread again. So let's run it also. Let's uncomment that and run it. So as you can see that we are now running 3 threads, right? Our main thread, our thread that we have created using a thread class, and our thread that we have created using a runnable interface. Now let's go to another one. In this case, right, my thread and my runnable, in this case, the method that we are using, it does not return anything, right? It returns void. But if we want to return something, what we can do is we can use a callable interface, right? Here we are using a callable interface, and if we want to return some result from that method. So for example, in this case, we are using a callable interface, right? That's the only way actually to create a thread in Java that returns your result. So we are implementing a callable interface, which takes in this case a string, right, as a parameter. Which takes us a string, and we are returning a string here. And in this case, we are just simply returning hello from Callable. So now let's go and create a Callable. Again, let's uncomment this. And here, what we do is we are creating an executor service. We are going to talk about it a bit later. So we are just creating a single thread executor. So what we do is we are creating a myCallable, a new object. And what we do is we are passing that object to our service. So we are submitting that the callable that we have to our executor service. This is, and so far this call is asynchronous. So this call is asynchronous. So what it means is whatever logic we are going to add here, this logic will run in parallel to whatever logic we put here, right? It's asynchronous. But this call is synchronous. So what it means is when we get the future get, so what it means is it will block this call, it will block this thread, and will wait at the result of that future. And in this case, as a result, we will get whatever the value we are returning from the string. So let's run it. Now, as you can see here, we have the first way, right? First way of creating a thread is just extending our thread class. The second way is to implement a runnable interface, and if we want to return any result from that thread, we are using a callable interface. Let's take a look at the thread lifecycle in Java and what kind of states that we have. For example, in this case, what we do is we are creating a new thread, and let's call it T. And after that, we put that thread to sleep for 1 second. Next step is that if we take our thread's state at this point, it will give us as a result new, because that thread that just created, it's not running yet. So at the next step, what we do is we are starting a thread, right? Again, if we start a thread, it doesn't mean that it immediately starts to run. So what happens is that actually JVM delegates the responsibility of the thread running to the operating system. How exactly that happens? So in this case, we are creating a JVM thread, right, at this point. So what happens is that the JVM maps that to the operating system thread. How exactly that happens? JVM calls the native code using the GNI, and in the, for example, native code for the Linux, it's pthread. For the Windows, it's create thread, and the operating system creates the operating system level thread, right? So, and the operating system scheduler, what it does is that this scheduler schedules when that particular thread, in our case this T thread, right? When that thread should run. And it assigns, let's say that our CPU has 5 cores, right? And all cores are taken, and the OS scheduler is assigned to the first core that this particular thread to run. It doesn't mean that this thread will run and complete its work on the first core, right? It moves the thread run between the cores, and that's it. After it's completed, after thread is completed, what we do is we are calling the join here. What join does is it makes sure that our T thread our main thread will wait until our T thread finalize its work. If we run the state at this point, right? If we run the state at this point, get state, then we will get the terminated state for this thread. Let's run and see that in action. Okay, as you can see here, first we are creating our thread. It's in the new state. Then we are running our thread. It's in the runnable state, and the scheduler decides that when that thread should run. And after the thread is finalized, then it's in the terminated state. There are two kinds of threads in Java, the user threads that we have been using so far, and another kind of threads that we have in Java is called the Daemon thread. So for example, let's say that we are creating a thread, here a new thread, and what we do is we are just printing that the Daemon thread, and we are putting that to sleep for 500 millisecond, and we are doing that in the while loop. So which means that this thread won't quit, right? This thread won't finish its work. So it's gonna run endlessly. So, and the next thing is that we are making this thread as a daemon, right? So we are setting the daemon to true. So what's the daemon thread? Daemon thread is the low priority thread. It's usually the most famous usage of it is it's used for the garbage collection. So for example, in comparison with the user thread, right? JVM waits for the user thread to finalize its work. It doesn't quit, and it waits for the user thread to finalize its work, but for the daemon thread, it does not. If the main thread finalizes its work, then JVM will just shut down without waiting for the daemon thread. So for example, right, in this case, daemon thread should run endlessly, but in this case, it won't. As soon as the main thread is finished, then the daemon thread also will stop. So let's run and see that. So let's run this one. So as you can see here, our JVM quits. The reason is that the daemon thread is a background thread. It's usually, as I said, right, it's usually used for things like garbage collection or similar kind of works. Another thing is that what we have for thread is that we have a priorities for thread. Threads can be in the minimum priority, in the normal priority, and in the maximum priority. So we can assign, let's say we have 5,000 threads and we want them to be run, we want like 5 threads to be run in the maximum priority, right? Usually when the threads are created, the priority that is assigned, let's see that, right? For example, here, let's say that for daemon thread, let's assign set priority, right? Set priority. So we can assign the priority here, let's say maximum priority, right? We can assign the maximum priority here, but when the thread is created, it's usually assigned as by default the normal priority. We can assign the maximum priority for it to be run in priority, but it's not guaranteed by the scheduler because we are delegating that responsibility to the operating system scheduler, and it's not guaranteed that if we set for the thread the priority to maximum, it will be run in priority to the other threads. Let's take this very simple example and understand what is the race condition and the data inconsistency in Java, in multithreading. So for example, let's say that we have one variable here. So we have a class race condition demo, and here we have one static variable counter. And so what we do in our main method, so we are creating one runnable. So what runnable does is it just increments the counter, this variable, right? Counter, it increments that 1000 times. And we are creating two threads, thread 1 and the thread 2. And we are passing this runnable here, so this thread 1 and the thread 2 will do exactly the same task. They will increment the counter 1000 times, right? So we are starting both threads, and then we are calling a join, which waits until our main thread will end, right? So we are waiting until T1 and the T2 will finish. So what we expect here, what we expect as a result of this operation. So we expect that, okay, we have thread 1 that incremented it 1000 times. We have thread 2 that incremented it also 1000 times counter, right? So as a result, we should get the 2000. So now let's run it and see that do we get 2000 or not? Yes, we get the 2000, but let's increment. Let's add it. Let's make it not 1000, but let's make it 10,000. Let's make it 10,000 again. So thread 1 increments it 10,000 times counter, and the thread 2 increments also 10,000 times. We are expecting that this counter will be incremented by 20,000, right? 20,000 first thread and 20,000 the second thread. Let's now run it and see that. Okay, the result is unexpected, right? It's a 12,457. Let's run it one more time. Let's run it one more time. Again, the result, every time when we run this, the result will be different. Why it happens? So why this, for example, this one, right, getting close, it's a 19,952. Why we are getting this unexpected result? The reason why we are getting that, because in this case, we have one shared we have one shared variable that is shared by the thread 1 and the thread 2, and they are updating this variable inconsistently. So what's that mean? So let's go and see that what exactly happens when we are updating that variable. So what we do from our side when we write a code, right? We just write it as a counter plus plus, which is that we are incrementing the counter. From the compiler side, compiler doesn't do this operation. From the compiler side, compiler just takes the counter and adds 1 to the counter. But what exactly happens from the CPU side? From the CPU side, this operation, the simple counter incrementing the counter, it's actually divided into the CPU performs that into 3 steps. What are those 3 steps? The first step is that the CPU loads the value of the counter from the memory into the CPU register. And the second one, it increments the value in the CPU register and then flashes back that value back to the RAM memory. So if we go to the visualize that, how exactly that happens, so we have a RAM memory, right? In the RAM memory, we have a counter. Let's say the value of the counter is 0. So how the CPU is organized? So let's say that we have a CPU with the 2 cores for the sake of simplicity, right? And each core with thread 1 is running in the first core, and the thread 2 is running on the second core. So with what we have in each core, right, in the CPU. So we have a registers, we have levels of cache, right, in the CPU. So we have the first level of cache, second level of cache, and third level of cache, and we have registers. So what happens? The first one is that this value, right, counter for each thread 1 and thread 2, this value is loaded from the RAM into the CPU register. So it's in the either threads are keeping them in the first level of cache, a second level of cache, doesn't matter, but they are loaded into the register for the first and the second one. And then each one, in each register, we are incrementing that value. Then we are writing back, flashing back that value, right? Whatever we are keeping that in the cache here, in the L1 cache, L2 cache, we are flashing back into the RAM memory. So what happens? What happens is that, let's say that the value is initially 0, right? So a value is initially 0, and the thread 1 is set that value to 1. And what we expect is, if the second one will do the same, right? Second one should increment that, should make it 2, not 1. But what happens is, since it's loading from its cache to the memory, it just overwrites that value. So that value, this counter value, right, is 0. It becomes, so we are expecting that T2, right? T2 will make it 2, right? Will make it 2, but actually it overwrites that value, because for T2, that value is still 0, right? That value is still 0, and it overwrites that value. So that's why we are getting this unexpected result, and that's why we call it race condition, because we have one shared field, right? That is shared by both threads, and that they are overriding each other's value. So that's why we are getting this unexpected result. So how we can do that? Usually in, let's say, large projects and so on, so usually what we do is we are trying to avoid to having because if we know that that resource might, so if we know that it's not thread safe, so in that case we just try to avoid to have global variables. If we have to have them for one or the another reason, then we are using thread safe operations. For example, we are using synchronized and other operations which we will look in another episodes. In previous episode, we have seen that what is the race condition in Java and what kind of problem it creates. So for example, in this case, we have one shared field, private static counter, so which is accessed by 2 threads. So what we do is we are creating 2 tasks, and for each for what we do in the task, right? So we are incrementing. In each task we are incrementing the counter 40,000 times. So we are creating one thread and we are passing the task, and we are creating another thread, and here we also passing the same tasks. And in the previous episode, right, we have seen that if we are incrementing that here, if our counter is here, then in that case, what will happen is we will have a race condition, and this result is unpredictable. So let's run it and see that one more time. So our expectation is that this value will be 80,000 because the thread 1 increments it 40,000 times, and the thread 2 increments it 40,000 times. We expect that this value will be 80,000. But in our case, it's 44,706, and every time when we run it, the result is different, and we're getting unexpected result because of the race condition, which I have explained in the previous episode. So one of the way how we can solve this problem, we are adding a synchronized block, right? Or we are adding synchronized keyword to our method. So what happens is, if we will run this method again, we will run our main method, always we will get the result as the 80,000. So what happens is, we have moved this increment part, right? This increment part of the task, we have moved that to the separate method, and we marked it with the synchronized keyword. What this synchronized keyword makes sure says, synchronized keyword makes sure that each thread, so let's say we have in this case 2 threads, right? We may have more, 5, 6, or whatever. So this method is only accessed by one. It only accessed by one thread at a time. So let's say that if thread 1 accesses the increment, then in that case, thread 2 cannot access it. Thread 2 should wait until the thread 1 finishes its work, and then after that, thread 2 can access the increment method, and vice versa. So doing that, we make sure that we exactly increment that 80,000 times, and our result is always predictable. What's the downside of it? The biggest downside is always slow, because one thread is waiting for another thread to finish. Actually, it's the same as if we will run in this specific case, if we will run incremented 80,000 times instead of separating that work to 2 threads. That's how it happens. But let's also take a look how it exactly happens under the hood, right? So what happens under the hood? Under the hood, what happens is JVM creates a class so-called the monitor, which has the key to that block or to that method, which is synchronized. So what that monitor has? The monitor has the conceptual, right? It's not exactly pseudocode wise. It has 3 fields. This first one is the owner thread. It's basically the thread that is currently accessing that synchronized block or method. Another one is the entry queue, is the which method, which thread is the next in the queue that will access that part of the code, right? It's we are adding that to the entry queue, and also the threads that are in the wait list, so that called the wait method. So we are adding them to the wait set. So what happens? Let's go step by step, right? So in the first step, let's say that we have started thread 1 and thread 2. So what happens is thread 1, let's say that got the key, and the thread 1 is the owner of that thread. So in that case, T2 also wants to access that. T1, the monitor is owned, the owner of the owner thread is the T1, and the T2 also wants to access that method, right? So what happens is that the T2 cannot access that, because that already, the monitor can have only, key can be owned only by one thread at the time, right? So only by one thread at the time. So what happens is JVM adds the T2 to the queue, right? Because it will be next one in the queue that will run that method. So it adds that it calls the monitor entry queue, and adds that thread T2 to the queue. So what's the next one? The next one is that the JVM calls because whenever we are in the multi-threading, right, JVM works very closely with the operating system threads. So it's calling the operating system functions. So in this case, right, let's say that we are using Linux, and in the Linux, what happens is JVM calls the futex wait method of the Linux. So, and the operating system puts the T2 to the block state. So operating system blocks the T2, because T2 cannot run right now. And if let's say that there is there is a core that is assigned to the T2, it's freed by the OS scheduler. So OS scheduler frees that core. Let's say we have only two cores, right? Core 1 and the core 2. And the T2 is running on the core 2. Operating system frees that core because it's because T2 is in the block state, right? So and the next one is, let's say that the T1 finished its work and the T1 releases the monitor or releases the key to that method. In that case, JVM picks the T2 from the queue and the JVM calls the futex wait operation of the Linux. And then in that only after that, operating system marks T2 as a runnable, and the OS scheduler eventually schedules T2 to run on the one of the CPU cores that are available. So that's exactly what happens when we are using the synchronized keyword, right? So when we are why it's important to know that, because when we are, especially in the multi-threading Java, right, we need to know that how exactly JVM works with the operating system, because how operating system scheduler schedule to run those threads on the cores. We need to know those in details, otherwise we may get some unexpected results. In previous episode, we have seen what is the race condition in the multi-threading and how we are resolving that. So for example, in this case, we have a very simple example. We are creating a two thread, and each thread, what it does is, each thread increments the counter 40,000 times. So how we make sure that we are correctly incrementing that? So what we do is we move the counter into the increment method, and in the increment method, we make sure that and we added the synchronized keyword. So we make sure that this method is accessed only by one thread at a time. So what happens is that the JVM creates a monitor, or let's call it a lock, which can be accessed only by one thread at a time. Only one thread at a time has a key to that lock. So that way, using a synchronize, we make sure that we get the predictable result. That's one way how we are resolving the race condition. Another way is to create explicitly lock here. So for that we are using locks from the concurrent library. So one of the locks is the ReentrantLock. So what we do here, we are creating a lock, and the logic that we have here, right? Instead of using the synchronized keyword, what we do is we are explicitly creating a lock, and we are locking when we access this method, and we are incrementing the counter, and then we are unlocking. So we are releasing the key, and another thread in the queue can access this method again, can access this part of the method. So what's the advantages of using the lock instead of the synchronize? One of the advantages that I see is that, for example, here, right, let's say that we have another logic, and we have some logic prior to the lock, and we have another logic after the lock. So that logic, for example, prior to this one, right, it can be performed we can only lock the part of the code that we want to be accessed by one thread at a time. So that is the one advantage. Another advantage is that this lock class, ReentrantLock, has a lot of methods, a lot of useful methods that can be used, for example, try-lock and the similar. That's the one way, and that's the one way. One class in the locks library. Another one that we have here is the ReadWriteLock. So what's the ReadWriteLock? The ReadWriteLock is that, as by name you can tell that ReadWriteLock is that we are separating that reading and writing to some data or some shared resource. We are separating that to two methods. For example, in this case, we have, let's say, again, shared resource, or let's call it a data, and we are writing some random value to that data. So, and we have two methods, write, which is that we are writing value to that data, and the read, that we are reading value from that data. So this read method here, it can be accessed as many threads as possible. So for example, in this case, what we do, again, we are creating a ReadWriteLock, ReentrantLock, and we are acquiring a lock, and we are performing some operation. In this case, we are just printing value of the data, and we are unlocking that, right? So that's the one way. So that's how we are doing the read. And what's the advantage of it? This read method, it can be accessed as many threads as possible. For example, 50 threads at a time can access this read method. But if the, let's say, 51st thread is accessing the write, in that case, all the subsequent threads, they will be blocked. Doesn't matter, read, write, and all of them will be blocked until the lock is released here. So that's the advantage of using the ReadWriteLock, because let's say that our class or our application is read heavy, then in that case we can use here reentrant ReadWriteLock. So let's run it and see that what we are doing here. In this case, we are creating two runnable, right? The writer and the reader, and we are starting two threads. One is the writer and the two readers. So if we run this, we can see that the first what happened is it can happen. Let's run it one more time, and it can happen also in reverse. So readers, they can access that shared resource, so they can run in parallel. But once the writer accesses that log, so these two threads are blocked until the writer releases that log, right? Let's run it one more time. Okay. Okay, for example, in this case, right? Let's say that in this case, we have, so first what happened is, lock is acquired by the writer, and the writer accessed the shared resource, and all the subsequent threads, thread 1 and thread 2, blocked until the lock is released. But after the lock is released, it can be accessed by as many read threads as possible. Wait, notify, and the notifyAll is a way to how to synchronize work for two or more threads in Java. So let's take this very simple example. So let's say that we have a message which has two fields, right? Content and empty. And we have two threads. One is producing message, which means that the one thread is that writing, one thread is that setting some value to this content, and another thread is consumer. So which is that thread is reading from this content. So you can imagine it as a queue. So let's say that we have a queue, and one thread is adding message to the queue, and another thread is reading from that queue. This one is the first thread is that the producer, right? It produces message, and another one consumes the message. So what we have in this method, right, put, that we are setting value for the content. So it's used by the producer thread. So what we have here, so what we do as a first step, we are checking that besides the content, also we have one more field, which is the empty. So we are checking that if the queue is empty, which means that if the content is empty until if it's not empty, then we are setting a value for it and the setting empty to false, right? But if it's not empty, then in that case, what we do is we are waiting, right? So we are just printing producer is waiting, and we are calling a wait. We are calling a wait method. So wait method is in the object class. So every class by default extends from the object class implicitly. So we are calling wait. So which means that thread, whatever thread is calling this put method, it will wait. It will wait until the message is consumed by the consumer. So after it's consumed by consumer, again we are setting the message here, and we are setting the value to false, which means that it's not empty anymore. Consumer can start to consume, and after that we are producing whatever message that we have just produced, right? Whatever message we have just set. And the next field, what we do is we are calling a notifyAll. So what notifyAll does is notifyAll wakes up all the threads that have been put to sleep. So for example, right, when we're going to understand more when we go to the take, which is the producer, which is the method that is called by the producer. So basically the idea is that we are, if any thread is put to sleep, so we are notifying those threads to wake up and to do the work on their side. So the another one, this is all for consumer, right? So when we are consuming messages and we are putting the messages into the queue, or in our case, we are just setting value in the string. So another method that is called by the consumer is take. So here we are doing exactly the same, but instead of producing, here we are consuming. So here what we do is we are checking that the if message is empty. If message is empty, which means that there is nothing to consume, right? The consumer is waiting. So again, we are calling a wait. So we are calling a wait here, and after producer has produced the message and set that empty to false. So what we do is we are going here and we are setting to empty to true, and we are consuming that message and we are printing that. And after that, again, we are notifying the producer that okay, the message is consumed, so now you can proceed your work. And we are returning here, so whatever the content is here, right? So again, why we are doing that, right? Wait and notify is just a way of synchronizing work between producer and the consumer. Let's say that we may have one producer and many consumers. That's why we are calling here notify all, or vice versa, right? We may have one, or we may have many producers and many consumers. That's why we are calling notify all. We have also notify method that is available, which wakes up one thread at the time. So again, we have seen that in the previous episode, right? So what happens is when we are starting our threads, so when we are here, right, we have added the synchronized keyword. So we have added synchronized keyword. So what it does is, so by default, our thread is our main thread. In our case, it's wait and notify demo thread. So what happens here is that we are creating one, so monitor is created, or lock, and which has the several fields, right? One of them is the owner thread, the thread that is currently owns has the key to the lock. Another one is the entry queue, and the next one is the wait set. So here we are adding threads that has been put to sleep or has been put to the wait mode. So when we are calling the notify all releases all the threads that are in the wait mode here. So that's it. And in our main thread, so what we do, right? We are creating a new message, and we are creating two threads. One is the producer, which produces the messages, one by one. Hello from wait notify demo, and then it puts the messages, sends the messages to the, adds the messages to the queue, or we're just calling the message and putting the message. So we're producing the message, and after that we put that to sleep. We put the thread to sleep for consumer to wake up. And in the next one, so what we do is we are in the consumer, we are taking the message, and again we are putting that to sleep for the producer to wake up. So let's run it and see that what's going to happen. Then we are starting producer and consumer, our two threads, right? So we are starting two threads, as you can see here. So what happens is, first producer produces hello, then goes to wait mode, right? So goes to wait mode, and then consumer consumes the message. Producer produces the message, then goes to wait mode, and then notifies the all other threads that are in wait. So then consumer wakes up, consumes the message, and then consumer wakes up the producer, and the producer again produces the message, goes in the wait mode, and wakes up the consumer, and so that goes in circle until we have produced and consumed all the messages.
To understand volatile keyword in Java, let's take this very simple example. Let's say that we have a main thread, and in the main thread, so what we do is we are starting another thread, let's call it T, and in our thread, we are setting the while the running is equals to true. It's a global variable here, and while it's true, then we are just waiting, right? And after running is set to false, only after that we quit this while loop, and we are printing that it stopped, right? So we are printing that this thread has stopped. So the next one is in our main thread, we are starting our thread T, and we are waiting for 1 second. And only after that we are setting this value to false. Let's run it and let's see what's gonna happen, right? Let's run it and let's see what's gonna happen. What happens is, as you can see here, this thread, this program, right, which has the 2 threads, it's run indefinitely. It never stops. Let's wait a bit more and make sure that it doesn't stop. So it doesn't stop. Let's stop it. So why it happens, right? Why it happens? Why that this thread, we set this value to false. We expect that since it's a global variable, we expect that thread T also will see that value and will stop while loop and will exit and will print it stopped. This happens is, let's look at the architecture. So what happens is that on the CPU and the RAM level, right? Let's visualize that. So let's say that in our RAM memory, right, we are creating one variable, running is equals to true, and we are starting 2 threads. So let's say we have a CPU with only 2 cores, and in the first core, so what we do is in the core 2, we are main thread is running, and we are updating value to false, and we are updating our CPU cache, and we are also updating in the RAM, right? We are updating that to false. But for another thread, for the thread T may not see that value because thread T takes the value. Thread T, when it starts, it takes the value from the RAM and it caches in the CPU. So when the thread 2 changes that value, thread 1, right? Thread T may not see that value. So for that visibility, so for making sure that when we are changing a variable and the variable is changed in the RAM, to make sure that the visibility is the same for all, meaning that the thread 1, thread T, right here, thread T will also see that, we are adding a volatile keyword. So let's add here volatile keyword, and after adding volatile keyword, let's run it one more time. Now, as you can see here, it stopped, right? So that's why I put the comment here that without volatile thread may never stop. So meaning that these 2 threads may not see each other changes unless we are adding here volatile. Again, let's revisit that. So what we have here, right? So we are in the main thread, we are changing the value, and we want to make sure that that change is visible to other threads. So in what it does is what the volatile does is volatile writes back that value to the RAM, and it also makes sure that every other thread that is running sees that the latest value. But volatile only enforces the visibility. It doesn't enforce the atomicity. So atomicity we have seen earlier. So let's say that we have here not Boolean, but we have here int. Let's say that the count, right? We have here count, and the count is equals to 0. And if we are incrementing this value count, right? If we are incrementing that in the thread, that operation is done. So let's say that here we are incrementing that, right? So we are incrementing here, I'm busy watching. So let's say that, busy wait, and let's increment the count. Let's increment the count here, and we are incrementing the count. Let's make it static here. Static. So we are incrementing a count. This operation still will be done in 3 steps, right? I have explained that already in the synchronized episode. So this operation, we are loading that from the RAM, we are incrementing that in the CPU register, and we're writing that back. So this operation is still done in the 3 steps, and for it to be atomic, we still need to use the synchronized keyword. Again, volatile only makes sure that the visibility, only makes sure that the latest changes, as we have here, right? The latest changes is visible to all threads, but it doesn't guarantee the atomicity. For atomicity, still we need to have the synchronized keyword, which you can see in previous episode. Modern CPUs and the compilers reorder instructions for better performance. They also keep the values in the CPU cache, which may not be updated in the RAM memory, which causes the issues in some cases. So for example, issues like a race condition that we have seen before, visibility issue, or the atomicity issue, all these may happen in the multi-threading environment. So what happens is that in Java, we have the Java memory model, which basically is the set of the rules, and one of them is the happen before relationships. It ensures that the visibility and the ordering operations across thread. So what's that exactly mean? So let's go step by step and understand. The first one is that the program order rule, right? So what program order rule says is within the single thread, statements appear to run in order. So for example, let's go here and see that what exactly it means. So in this example, we have in the main thread, we have two variables, A and the B. A, we are setting value to 10, and in the B, we are setting the value of A plus 10. So we expect that when we write this program, right, we expect that the value will be printed, A will be printed 10, and the B will be printed 50. So what Java memory model does is it ensures that this one writing to A will happen exactly, the order will be happen exactly the way that we put that, right? Imagine that the CPU has reordered that. So what will happen in that case is that we, for the B, we will get the value of 5, which is not expected for us, right? Which may create a confusion and basically may create unexpected result in our program. That's the first rule that defined in the happens before. What's the next one? The next one is that the monitor lock rule, right, in the synchronized. So we have seen that before in the previous episode, but let's go over it one more time. So as rule goes, unlocking a monitor happens before another thread locks it. So what exactly that means? So let's go and see another example of synchronized. So here what we have is we have a counter class, and if we go here we have a field count, right? In the count, so what we do is we are counting. So we have two methods, increment and the get. So increment and the get. So in the increment we are incrementing the count, and in the get we are getting the whatever the count value is right here. So as we have seen in the previous episode, this operation increment, right? It's not just increment, it's divided into 3 steps, right? The first step is we are reading the value from the RAM memory. In the second, we are in the CPU register, we are incrementing that value, and in the third, we are writing that back to the RAM memory. So we want to make sure that the releasing the lock, right? And by default, every thread is creating a monitor or a lock. And when we are put the synchronized keyword, right, in the method, so access to that monitor or access to that lock, the key to that lock can be only obtained by one thread. So what we make sure is that the lock, happens, this operation, right? This whole operation happens before the releasing lock. So basically, we release the whole operation, and only after that we release the key, and we are releasing the lock for this operation. And that's the first part. And the second one is that here, right, for the get count. So we make sure that this happens after we are acquiring the lock. So what will happen that if we releasing the before lock, so which means that this operation may not be atomic. That's the first problem. And also if we acquire the lock, if we are acquiring the lock before, so if this operation happens before acquiring the lock, so we may get result here. The result that we get here it may not be the latest result, right? So that's the second rule that we are defining in the Java memory model. Let's go to the third one. What's the third one? The third one is that the volatile variable rule, right? So as it goes that the volatile variable rule, write to a volatile happens before a subsequent read. Let's go and see this example. Let's take a look at this example. So here what we have two threads. The thread writer, so what the thread writer does is it sets the value to the number, which is a global variable, to 42, and it sets the value to true for a, again, global variable, which is the ready. So ready is the volatile. So what it means is the changes that is made to this variable, it will be seen by all other threads, right, in our program. So, and we want to make sure that the read of this variable ready, it will be, so write to that will happen where it happens before the read, right? The happens before rule here is that it happens before the read. So otherwise, this will read will see that the old value of the ready, and it will not go further, right? It will not print the result here. So that's the first one. And another one is that we have number here, which is not the volatile, right? But here, if we set the value to true, so whatever the value comes before it, whatever the variable comes before the ready, those variables also will be flashed to the RAM memory. So for example, in this case, if we print the number here, right? If we print the number will give us 42. Let's run and make sure that it works as expected. Yes, you can see here the number is 42, because in this case, that it's not that it will happen before, it happens before the read. That's the first one. Also, all variables that come before this variable that is volatile, they also will be flashed to the RAM memory. So that's the rule for the volatile. Now let's go to the next rule. The next rule is that the thread start rule, right? Thread start happens before actions in that thread. So let's go and see the example of the thread start. So what we have here, we are in our main method, we have one variable, data, let's say, right? It's a global variable, and we are setting that value to 42. So we make sure that it happens before the thread start. So, right? So setting the value to the 42, it happens before we are starting this thread. So otherwise, what's going to happen is we will see the value here 0, right? But we want to, because when we write this program, we expect that the value here will be 42 because we already set that here to 42. That's why it happens before the thread start. So let's run this, and as we can see here, the value is 42, and the Java memory model makes sure that happens before rule also works here. So now let's go to the next one. Next one is that the thread join rule, right? Thread join rule is the all action in a thread happens before another thread returns from join. So let's go and see exactly what does that mean. So let's, for example, in this case, we are creating a thread and we are setting the result to the 99, and 99 is a global variable, so we are setting the value of for this variable result to 99, and we make sure that this happens before the join, right? So because here when we print the result, we expect that this thread already will finalize its work, and we'll set that to 99, and we will see here the value of the 99. So let's run it, and as you can see here, main thread sees the result of 99. So again, this one, right, this one happens before this join statement, which means that before this thread finishes its work. So let's go to the next one. The next one is that and now our final rule, which is that the final field rule. So final field rule, it's a write to a final field in a construction happens before reference is published. So let's go and see. So for example, here we have created a config. So let's go to the config and let's see what we have here, right? We have one field, it's a final, and we are setting that value to 100. This one happens before publishing the reference to this variable, right? So what it means is here, right, in the writer thread, if we are going to, we are creating a config, and here we are creating one config, and we are creating one config here, a new config, right? And when we are printing this value, we make sure that this one, right, this setting the value to the final, it happens before publishing the reference. So here we are publishing the reference to so here we have the reference to that field, to the size. We make sure that this happens, so setting the value happens before we are having a reference to that field. And that's for the write. And for the reader, we here, right, we already have the reference to that size in the config class. So let's run it and let's see that it works exactly as we expect it to work. Again, reader config size is 100 and the config created with the size of 100. So that's it. That's all the rules. It's not the complete list, but it's the main rules that we have for the Java memory model. It's again, Java memory model it makes sure that when we write a program, because when we write a program, we have certain expectations, right? We expect that certain rules for the locking and the unlocking. So we have certain rules for the visibility. We have certain rules for the thread start, for the thread join, for the final field. Without Java memory model, the CPU and the compiler, it just will optimize the code, and we may get the unexpected results. Usually, instead of creating threads manually, so what we do is we are relying on the executor service from the concurrent library to do that for us. So for example, in this case, we are using executors, and we are calling a new fixed thread pool. So we are creating a thread pool with the some number of threads. For example, in this case, we are creating only a thread pool with the 3 threads. So why we are doing that? Let's say that we have an example. Let's say our application is accessing database, and we can only open 100 connection at the time to the database. So we need to make sure that we have at most 100 thread accessing database at the time. So for that, we are using a thread pool. So in this case, we have created ExecutorService with at most 3 threads running at the time, and here we are creating 5 tasks, right? So execute, and we are submitting those tasks to our executor. So executor, it takes, so you can see here, it takes as an argument, it takes the runnable task. So we are creating a simple task here, and our task is just print the task number and print the current thread. So we will only create, as a part of this program, we will only create 3 threads, which will perform 5 tasks, right? So the first 3 tasks will be performed by the threads. Then after that, as soon as the thread finalizes its task, it will pick up another task that is in the queue. So let's run it and see that. So for example, as you can see here, right, we have created only 3 threads, thread 1, 2, and 3. And they are executing the task. They executed the first task, second task, and the third task. As soon as thread 1 or thread 2 finish the task, it takes another task from the queue. It takes the task 4 from the queue and finalizes it the same way is the thread 3. It picks the task from the queue and finalizes it. So if we can add here more, right, but the thread size won't change. We will have 3 threads that are working on those tasks and finalizing them. So far, we have worked with the only threads that are not returning any value. Let's work with the threads that will return some value, and we are going to use that. So for that, we are using a callable. So what we do here is, before using a callable, so what we do here is we are creating an executor service. We have talked about that in the previous episode, and we are creating a thread pool. So basically what it does is it gives us a thread pool with the 2 threads, right? Doesn't matter how many tasks we will submit to this executor service, it will use only 2 threads. The next one is that we are creating a callable. It's similar to Runnable, but with one difference is that it returns some result. So we are creating a callable and we are putting that thread to sleep for 1 second, and after that we are returning the value of the 42. The next one is that here what we do is we are to our executor service, we are submitting our tasks. So basically this starts our thread. So this starts our thread, and in the next line, right? So in the next line what we do, we are just printing that doing other works. This call here, it's asynchronous. So what it means is that whatever the work, whatever the logic we put here, right? This can work, this logic can work as asynchronously, non-blocking of the rest of the code. So for example, in this case, let's say that we have here we are just printing, but let's say we have here much heavier logic here, right? So in that case, again, this logic will go on in parallel with the whatever logic we put in our this thread, right? So it's asynchronous. So it's asynchronous, but what we do, it's asynchronous, or you can call it non-blocking code. So what we do in the next operation here is we are from the future we are waiting for the result, right? So we are waiting for the result. At this point, it becomes blocking, because at this point it waits our thread, right? Our thread, they are no longer asynchronous. It waits until the callable, until this thread finishes its work, and only after that it proceeds. After that, we are just printing a result, whatever the result we are getting here, and shutting down the executor in order to not to waste the resources. Let's run it. Let's see that it works. So as you can see here, we are doing some work while this thread is running. So we can put some other logic here. It's a non-blocking, it's a synchronous call, and then after that we are printing the results. Can we do better than that? Can we do better than we have here to improve this logic here for blocking the code? Yes, we can do that, and for that we are using the completion service. Again, we are creating a thread. We are creating executor service with the thread pool with the only 3 threads, and we are passing the executor to our newly created completion service, and more specifically executor completion service. We are passing our executor. So what we do here, right? What we do is we are in our for loop, so we are creating 5 tasks, and we are submitting each task. So we are submitting each task to our completion service. So we are submitting each task, and in the next one, right, we need to print all of those. In the next one, instead of using the get, we are using from the service, from our executor completion service, take. So what it does is it takes it doesn't wait, it doesn't block, but it takes the whatever, let's say we have submitted here 5 tasks, right? Whatever task is complete, it doesn't matter in which order we have submitted them. So we may submit the, let's say 20th task, right? 20th task is completed first. So we are taking that from we are taking that task from the pool, and we are printing that result. So let's run it and see that it exactly works as expected. As you can see here, it prints that in order of result 1, 2, 3, 4, 5, but it can print also in different order. It can print like result 3, result 2, and so on, because here it's a relatively non-blocking code, right? Relatively non-blocking code, because here we are not taking we are not waiting for the specific task to complete. We are waiting here to any task to complete, and we are taking from the executor completion service that task, and we are printing that. And again, we are at the end we are shutting down our executor service. But it's better than the previous one. It's better than the get, because here it completely blocks. It waits until it finishes. but here we are waiting until any task finishes. It's still better than this one, but can we do even better than that? Can we improve? Yes, we can, and for that we are using executor completion service. We are using here the poll operation, right? In the executor completion service, instead of the take, we are using a poll operation. So again, here what we do is we are creating an executor service, and in the we are also creating executor completion service. We are passing our executor, and then what we do is we are simulating a web crawling for the 5 websites, right? Let's say that we have 5 websites, site 1, site 2, site 3, site 4, site 5, and we are crawling some information from them. So what we do is we are creating each task to our service, to our executor service. So we are submitting each task, and we are simulating the network delay here. So we are taking some random number and adding 500, and we are putting the thread to sleep for that amount, right? So for that amount, and after that, we are returning a value that fetch data from the URL, from the certain URL with after certain delay, right? So that's the task that we are submitting to our service. So the task we are submitting to our service, and at this point, right, we are going to submit all the tasks. At this point, we are submitting all the tasks, and each task creating a separate thread, and in the not separate thread, but we are using only in this case 5 threads. Yeah, in our case, for our specific case, it will be 5 threads it will create. But let's say that we have 10 threads. Then in that case, we have only 5 threads. 5 of them will be executed as soon as those 5 threads finished its work, right? But in this specific case, we are creating 5 threads, and each of them in parallel fetches the information from that URL. So at this point, we have submitted all of them. Now this part is the most interesting, right? This part is the non-blocking. So what we do here, we are creating one variable received, and we are creating a while loop, and we are exiting this while loop only after received is equals to 5, right, to URL size. So what we do is, instead of calling the take as we do here, because this is blocking, because if let's say that none of the tasks are completed, in that case it will still wait until at least one task is completed, right? So it's still blocking, but it's better than the callable future. So here what we do is we are calling poll. Poll just checks that if there is any task that is completed. So it's a non-blocking, right? It's absolutely non-blocking. If it's not null, then we are getting from the future that whatever is completed, and we are printing that, and we are incrementing the receipt. If it's not, then in this case we can go and do some additional work, right? So we can print no task ready yet, doing other work, right? So we can add here whatever logic we want. Again, it's to make it non-blocking. So and here we are just simulating some work. We are putting that to sleep to 200 milliseconds, and at the end we're just shutting down our executor, and the printing all tasks are completed. Let's run it. This one is completely non-blocking, completely asynchronous service, and as you can see here, right? So no task ready yet. So we have submitted all the works. So at this point, we don't have any task that is ready that we can process. So we can do some other work. So let's say that in our program, we may have some other things, we can optimize our logic in order to do some other works. And as soon as it's ready, so let's say site 5 is ready, right? So we are fetching that, and we are printing that. Again, we are waiting for the next one to be ready, and again, we are printing that, and we are doing that until all our tasks are completed. After all our tasks are completed, we are then after that finalizing our main thread. Let's take this very simple example. Let's say that we are creating here a runnable. Let's call it a writer. And what we do is we are adding in a for loop, we are adding to our map and to our list a value. So we are, for example, adding key plus whatever is the I, and the value whatever is the I, and we are adding to the list item I, right? And the next step is we are creating 2 threads, thread 1 and 2, and we are starting 2 threads, and we are waiting until those threads are finished their work. So As we have seen earlier, if we have a shared resource, right here we are using two shared resources, map and the list. So earlier we have seen that example with the integer. If we are using a shared resource, so then if we are using one, two or more threads, we may have a race condition. Previously what we did is we have solved that problem with introducing a synchronized keyword. So in the synchronized keyword, so what we do is we are blocking this part of the code or this part of the code. So whatever makes sense. So only one thread at the time has the access to that shared resource. So but that using a synchronized keyword is not optimized because it's usually slow. It blocks the whole code. It blocks the whole portion of the code. So only for one thread have the access to it. So instead of using the collection, regular collection, and the synchronized keywords, so what we do is in Java we have also concurrent collection, right? Which is that the thread safe collections. So for the map we are using, for example, here concurrent hash map, and for the list we are using copy on write array list. So if we run this, let's run this code and see that okay, for the key we have added whatever we want to add, right? So we have added key 0, key 2, 1, and so on. And for the list we have added again, we have added 2 item zeros because we are adding it twice, and the item ones, and so on. So what else we have, right, besides these two collections that we have just seen? So in the Java we also have for the map we have a concurrent skip list. For the set we have the similar thread safe collections for the queue, and for the list we have already seen. This is not the complete list, but it's the mainly used concurrent, mainly used thread safe collections in Java. But let's take a look how these thread safe collections work under the hood, right? So under the hood, what they do is they mainly rely on the CAS operations, compare and the swap. So they are also using a synchronized. They are actually using the synchronized in combination for the CAS, but mainly they are relying on the compare and swap operation. So let's take a look what is exactly compare and swap operation. So for that, let's take one simple example. So here what we do is we are creating atomic integer. It's the atomic integer. It's the way of it's a thread safe version of the integer, the same as we have the thread safe collections, and also we have a thread safe integer here, right? So we are creating here atomic integer, and we are creating two threads. And what each thread should do is we are calling a method. It should increment this value to atomic integer. It should increase that value to 5 times, and we are returning whatever results we are getting, right? So we are starting both threads. We are waiting until they are finishing their work, and then we are printing the final result, which should be 10 at this point. So what we do, the important part is what we do in the increment method, right? So in the increment method, what we do is, again, we are incrementing each of these threads for each of the thread, right? So we are incrementing the value of the atomic integer. We are incrementing that 5 times. But how exactly we are doing that? So here we are using the CAS algorithm. So what it does is, so first we are for the updated, we are setting that to false, and what we do is, while the updated is not set to true, so we are doing the following operation. So what we do is we are reading the old value of the thread. So here, right, from the atomic integer, so whatever the old value, let's say that the old value, we are just starting out, right? So we are reading that old value is 0, so we are reading that zeros, and we need to increment that once, right? So in each operation we need to increment once. So we are reading that value, and we are setting that the new value, whatever the value we want to update that to, right? And we are calling in the atomic integer compare and set. We are calling the old value, and we are calling the new value, so with the old and new value, right? So if that succeeds, so which means that if this operation succeeds, compare and the set, right, then in that case it will return updated, so which means that we are breaking that loop, and we are we are breaking that loop, so which means that we have updated that atomic integer once. If not, then we are doing that until we succeed. So let's take a closer look, right? Let's take with this example. So we have thread 1 and thread 2. So thread 1, so they are running at the same time, right? So thread 2 is running at the same time. So what we do is we are reading the value, old value, and both of them reads as 0. And then we are setting the new value. New value, we want to update that to 1, right? In both of these cases. So this one, right, it calls the compare and the set for 0 and 1, the thread 1. It succeeds because when it reads that value again, 0, and it sees that, okay, this is the equals to the old value, it sets that to 1 and it returns true. But this one, right, this the second one, it doesn't succeed because why it fails? Because when we are calling the compare and set, it reads the value, and it compares that value with the old value, and the value at this point is already 1 because this thread 1, thread T1, right, it's already updated that, and this value is already 1, so it fails, it returns 0. Then it starts the operation again, then it goes, that's why we set that in the while loop, then it reads that again. Now the old value is 1, and it reads the new value, it wants to set to 2. It does it until it updates that value, right? It does that in loop until it updates that value. But another question is, when you look all of this, you may think about, okay, that's clear, but how about this part, right? How we make sure that this operation is, how about this part, right? How we make sure that this operation is atomic? Because here we are sending the old value and new value, and we rely that the compare and set will read that again and will set that value. We make sure that this operation is atomic because usually, right, most of the CPUs have the special instructions, like for example, we have the special operations just for the compare and exphange, right? So we make sure that this operation actually, this will be atomic. So whenever we are reading the value, whenever we are reading the value again, so we make sure that that value is, that this operation will be atomic. So let's say that we are reading the value, and the value is at this point not, for example, in this case, right, the value is not 0 but 1. That means that another thread has already changed that value. Okay, let's run it and see that it works as expected. Let's run it, and as you can see here, first thread 0 increments the value, and the thread 1, and as a final result we get 10. So yeah, one more thing to add here. This operation, compare and swap, why it's preferred over the synchronize? Because it's called the optimistic lock. It doesn't block the whole operation. It relies on the loop, for example, in this case, on the while loop, in order to set that value. While in case of the synchronize, what we do is we are just blocking the whole, let's say that the whole block, or let's say that the whole method in some cases, just to make the update. So pessimistic lock, in case of in our cases, the synchronize, is much more slower than the optimistic lock, such as using the CAS algorithm here. Let's take a look at the synchronizers in the multithreading. So the first one that we are going to review is CountDownLatch. So what's that mean? CountDownLatch, by definition, it makes one or more threads wait until a set of operations performed by the other threads. So what's that mean? It means that, for example, in this case, we are creating a CountDownLatch with the value of the 3, which means that for 3 threads, right? So, and then every time when we are in our for loop, we are creating 3 threads, and we are decreasing the number of the countdown. So which means that we are decreasing the number of that we have initially created here. So the number is 3. So we have created 3 threads, and at this point, our CountDownLatch value is 0, right? So we say that after 3 threads is created, then wait. We are telling here to main thread that wait until these 3 threads is completed. So that's the purpose of this CountDownLatch. So if we run this code, so we can see here what happens is that the first 3 thread is performed. A main thread will do that anyways. Main thread will wait for these 3 threads to complete anyways. But let's say that we are creating one more thread outside of the main thread, and we want that thread to wait until these 3 threads is completed. So for that, we are using a CountDownLatch. The next one is that CyclicBarrier. So in the CyclicBarrier, so as the name suggests, we have some barrier, and we are waiting that all threads to wait in that barrier and then proceed. So for example, in this case, we are creating a CyclicBarrier with the value of 3, which means that the 3 threads that is reaching this barrier, they need to wait. And in our for loop, we are creating 3 threads, and then after that, we are calling barrier wait, right? So what's going to happen is each thread will start, and it will come to this point, and it will wait. It will wait until this value is reaches 3, and after that, all the threads will continue. So let's run it, and let's see that it works as expected. So let's run it. As you can see here, all 3 threads have started. They reached a barrier, and then all threads reach the barrier, and after that, we are proceeding with the other flow of the thread. And the last one is the semaphore. What is the semaphore? Semaphore is that, for example, in this case, we are creating a semaphore with the value of 2. What it means? It means that the only 2 threads will be able to perform at the time. So here we are creating 5 threads in the for loop. So here we have a runnable, and in the runnable we are acquiring a key from the semaphore, then we are performing some operation, and here we putting the thread to sleep for 2 seconds, and then we are releasing the semaphore. So, and we are creating 5 threads. So what will happen is only 2 threads will be performed at the time, and until the key is released, another thread won't be able to start. So for example, let's run it and see that in action. Let's run it semaphore. Let's run this semaphore demo. If we run it, so you can see here, first 2 threads acquired the key, they finished their work. After that, the next 2 keys acquired the key, they finished their work, and the last one is that our last thread acquires a key and finishes its work. Let's take a look at the fork join framework in multithreading Java and where we can use it. So for example, in this case, we have a very simple case where we have an array and we need to calculate the sum of it. So here what we do, we are creating a fork join pool, and we are invoking here pool, we are invoking, and we are passing here the sum that we want to calculate. So for that, we are creating a new object, a sum task, and we are passing our array start and the full length of the array, and we are printing the whatever result that we get here. So let's go to the sum task and see that what we are doing here. In the sum task, we are extending a recursive task, and here in our constructor, right? So what we do in our constructor, we receive an array start and end, and the main part is happening in the compute. In the compute, what we do for calculating the sum, we are, if the size of the array is less than 3 or equals to 3, then in that case, we are just calculating the sum and returning it. If not, then we are parallelizing the process. The way we do that, for example, here, right, we are taking the mid, and we are calculating the left side, and we are calculating the left side of the array, and we are calculating the right side of the array. Right side of the array, we are directly calculating that, but for the right side, we are asynchronously computing the left side. So here for that reason, we are calling a fork, we are asynchronously calculating it, and then we are calling a join, and we do that recursively, and at the end we are returning the result. Why it's important to know the fork join framework? Because it's used in a lot of cases. For example, in Java 8 for the streams and the similar, under the hood it uses fork join framework. Let's take a look what is the deadlock, lifelock, and the starvation in multithreading Java. So first let's start with the deadlock. In the deadlock, so what we do here in this example, we are creating two objects, lock1 and the lock2. And what we do is we are also creating two threads, right? In the first thread, we have two synchronized blocks. In the first synchronized block, we are getting the first lock, and then we are putting that thread to sleep for 100 millisecond, and then we have another synchronized block where we have a lock2 here. And in the same for the second thread, so what we have is we are acquiring a lock here in the first synchronized block, and then we are putting that thread to sleep, and then we have another synchronized block where we are using the lock1. So in this case, what will happen is that the thread 2 will never release the lock2, because we'll never be able to release lock2 because here it's waiting for the lock1, right? And the lock1 is in another thread. Another thread holds the lock1, and it also waits for the lock2. So for the first thread waiting for the lock1, second thread waiting for the lock1, and the first thread waiting for the lock2, and they are blocking each other. That's why we have here a deadlock situation. If we run this, as you can see here, if we run this, the first one holding a lock1 and the second one holding a lock2. So the second one waiting for the lock1, which is held by the first thread, and the second thread waiting for the lock1, and the first thread waiting for the lock2, and they are blocking each other. How about the lifelock example, right? In the lifelock, what we have is we have opposite situation where each thread is giving a way to another thread to perform its function, but they cannot complete. Both of those threads cannot complete their work. So for example, in this situation, what we have is we have a worker class, and in the worker class we have two fields, right? We have the isActive, and we have the active, and also we have isActive, which returns us whether or not current worker is active. And in the work, we are checking that if active is true, then in that case we are checking for the other active that is passed as an argument here. And if that is true, then in that case we are giving away to another thread and setting that to false and finalizing it. So for example, let's take an example. I think it will be more clear. So we are creating here two workers, worker 1 and worker 2. So in the thread 1, we are starting work for the work 1, but we are passing as other second work, right? We are passing the worker 2 as the work to do here as an argument. And in the second one, we are starting for the second worker, we are starting a work, and as a work, we are passing the first one, right? So vice versa. So what happens is here for each one, right? Each one will check the active is true, and each one will check that the other is true. So other, which means that for example, in case of the second one gives a way for the first one to perform, right? Because other is set to true. But what will happen is first one will go to this thread, it will print giving a way to the other thread to perform, and it will go to sleep for 100 seconds, and after that it will go to loop to check again. So basically they will never exit this loop, right? So they are giving a way for each other to finalize their work, but because of we have here continue, and because of this loop, they will never able to set this flag to false. Let's run it and see that it's exactly works as we expected. As you can see here, they are just going into loop, give worker 2 giving way to worker 1, and the worker 1 giving a way to worker 2, but they cannot complete their work. None of them can set their flag to false. So that's the situation where we have a lifelock. This is the real case situation that we may have in some cases. So we need to be careful to reorganize our work, not to have lifelock situation. And the last one we have is starvation. In the starvation, what happens is, let's say we have several threads. One of the threads get assigned. So for example, in this case, we have two threads, right? High priority and the low priority, and they are running indefinitely. So here, what we do is for the high priority, we are setting the priority to maximum, and low priority, we are setting to minimum. So what will happen is that low priority thread either will not get any chance to run, or it will get a little chance to run. So let's run it and see. So as you can see here, it's a mostly high priority, and the low priority thread gets a little chance to run. So mostly it runs the high priority thread consume all the resources. So that's an example of the deadlock, lifelock, and the starvation in multithreading Java. ThreadLocal is a way how to create in multithreading Java, how to, for each thread, have its own copy of that variable. So for example, in this case, let's say that we are creating two threads, thread 1 and the thread 2, and we want to each one of them has its own copy of an integer variable. We cannot just create here an integer variable, because in that case that will be shared by both threads, and as we have seen earlier, we may have conditions such as a race condition and others that which we have in the multi-threading environment. The solution for that in Java that is introduced is using a ThreadLocal. So in the ThreadLocal, what we do is, for example, let's say that we want to save an integer, right? So for the integer, what we do, we are creating one ThreadLocal with the parameter being the integer, and we are setting for the thread 1 its own value, and for the thread 2 we are setting its own value, 100 here and 200 here. And if we run this, as you can see here, for the thread 0 it's a 100, for the thread 1 for the thread 1 it's 200. But how it works under the hood, let's take a look how it works under the hood. So what happens is when we create a new thread is basically an object, right? It's created on the heap memory, and it has a name, and this is a priority, and so on. And one of those variables that we have in the heap as a part of that object, thread object, is a ThreadLocal. So we are introducing a new hash map here, ThreadLocal, where we are storing our values. And for each thread we are creating its own stack, so it has its own call frames, local variables, and the return addresses, and so on. But that's what happens under the hood, right? In our case, when we introduce a ThreadLocal, so what we do is, let's say we have created 3 threads, right? Then 3 objects are created on the heap. 3 thread objects are created on the heap, and each of them has a copy of has a field ThreadLocal which has a map, right? So we are here, let's say that we have a variable, whatever we call that variable, that's a local variable, right? So for each one we are setting its own value. That's how it's handled under the hood in Java. So going back to our example, in our example what will happen is, for each thread we will create its own ThreadLocal map, and in the ThreadLocal map we are going to store key and value, right? So for the first one we are going to store 100, for the second one we are going to store 200. That's it about the local thread and its use in the multithreading Java. Earlier in the episode, we have seen how we can create asynchronous code in Java using Callable, CompletionService, and now we are going to take a look to another way how we can write a asynchronous code in Java using completable future that was introduced starting from the Java 8. So what's the advantage of the completable future? I have here an example. One of the main advantages of the completable future is that it allows us to have a chain operation. So for example, in this case, let's say we have a scenario when we are when we are fetching a user info, we are simulating a DB call or the API call. So we are fetching the user info here. So we have fetched that. And after that, we need to perform another operation on this user, right? So we need to, based on this user, based on the username or user ID that we have fetched, the second step, we need to fetch the orders, right? Let's say we have an e-commerce application and we need to fetch orders. So based on this result that we have returned here, based on this user, we are fetching order for the user that we have just returned here, right? And the next one is we are fetching all the orders. So we have order 1, 2, 3, and here we are simulating some work. We are putting that thread to sleep. And in the last one, after we finalized these two operations, so what we do is we are, based on those orders, we are formatting the final output, right? So we are transforming result, and we are just printing that the user summary, name, and the orders. So as you can see here, so what we can do here, right? We can also add another, then we can add another apply, right? So that we can add, let's say we need to do one more transformation here, then we can add another apply, or then another compose, then another apply. We can do asynchronously. So completable future allows us to do these chain operations. As I said, it's a asynchronous code. So what it means is, while this one will be performed, while this code will be performed, so it goes to the database, it fetches the result, and based on that result, it fetches from another table orders, and then it formats that result to the result that we got to the final result. And while it's doing that, so it's a non-blocking, we can perform also other logic here. So in this case, we are just printing main thread is free to do other work. And after that, what we do is we are getting, so this part is blocking. So here we are waiting for our asynchronous code to complete, and we are printing the result here. So whatever the result is, here we are printing. Let's do that. Let's run this code and see that it works as expected. So as you can see here, it starts for fetching user from the database. While it's doing that, main thread proceeds with its logic, right? So let's say we have some logic in the main thread, and we don't want to block that. So we are going with the first one, fetching from the database, and then it proceeds to perform whatever logic we have after it, right? So then it proceeds with this logic, and after that we are completing our chain of the operations, and we are printing out the result. So that's the advantage of using the completable future. So we have seen so far Callable, we have seen CompletionService, and starting from the Java 8 also we have completable future. These are the ways how we can write asynchronous code in Java. But what are the other options, right? Besides this one that we have already seen. So well, there are not much options in terms of the standard library, but we have the external libraries that are specifically written for writing asynchronous code in Java. One of those libraries is Guava library, which is developed by Google's Guava library for listenable future. For listenable future, it was introduced before the completable future, and it extends future by allowing the callback when the task completes, and also it often used in the distributed system. So for example, here we have an example. We are creating a service. So we are creating a thread pool with the 2 threads. And here we are creating our listenable future instead of standard future. So we are creating a listenable future. And to that future now here, we can add, as you can see here, we can add the callback, right? So whenever this one completes, we want to see the result on success, what to do, or on the failure, what we need to do, what action we should take from our side. And so for the completable future, for the Guava, to sum up, it's a predecessor of the completable future. Nowadays, if we want to write a asynchronous code, so usually we go with the completable future. The advantage of Guava was that it was introduced before completable future, and in some cases it was used before. So in some legacy applications you may still see that. So also it's good for integrating async callbacks. Another framework, another library that is used is Netty. Netty is used for the high performance network applications, for example, for web servers. It's entirely based on the event loops and the async callbacks. Uses its own abstraction. It's called the channel future. So for example, in here I have an example where we are creating a channel future, and in the channel future we are adding a listeners to that future. So where it's used, right? It's used for applications such as gRPC, Spring Web Flux, and Akka. And it's a low level and very efficient. So to sum up what we have for how to write asynchronous code in Java, right? So let's start with from the very beginning. First, we have a thread, we have a future, we have completable future, we have Guava, and we have a Netty. So for those, do they support chaining? Are they non-blocking? And are we using nowadays either application or that from the out of the box, right? From the Java. So for the thread, it's chaining is not allowed. So it can be non-blocking, but we need to do that manually. And the modern use is rare. For the future, it doesn't allow chaining. It does not have it's blocking, and it's also, you can see that in the legacy application. Completable future allows chaining, allows non-blocking, and it's used in the modern applications. Guava again allows chaining and allows non-blocking, and it's used sometimes. So for the Netty, we have again it allows chaining, it allows non-blocking, and it's used in the high performance applications. So for recommendations, when we are decide for one or the other way, for one or the other reason to use a asynchronous code in our application, to use a completable future, it's because it's much more easier, and it started from the Java 8. Java supports completable future. Starting from the Java 8, it was introduced, and for the network IOs and for the reactive systems, we can use Netty. To understand reactive streams, first let's take a look at the event-driven architecture. For example, in this case, let's say that we have a user, and the user places an order, and the order system should notify the payment system, inventory system, and the shipment system about the order. So before the event-driven architecture, the way the systems used to interact with each other is order system used to call payment system directly and the inventory system and the shipment system directly. This introduced several problems which was solved using the event-driven architecture. So what we do in the event-driven architecture, right? In the event-driven architecture, in the center of our system, we have an event bus. So for example, it could be Kafka, it could be similar systems. When we are sending event to the event bus, let's say to the Kafka topic, and from the Kafka topic, we have three subscribers, right? We have a payment system, we have inventory system, and then we have shipment system. So we have one producer, and then we have three consumers. By the way, they can also be named differently. For example, in the Google Cloud Platform, the name is producer and the subscriber. Also, we have an observable, but the point is the same. So we are publishing message, we are pushing message to the event bus, and also on the downstream system side, we have several systems that are one or many systems that are consuming from that event bus. So as I said, we can have multiple producers, we can have multiple consumers. For example, in this case, let's say we have three order systems, right? And they are publishing to the event bus, and on the consumer side, we have three consumers that
consuming those orders. So this is event-driven architecture. Also, we are calling it reactive processing. So what's that mean in this case? Reactive processing means that our downstream systems reacts to the event. So we have event, and our downstream system reacts to those events. Also, in this case, in case of the event-driven architecture, or let's say that in the reactive processing, so what we have is we have a back pressure handled by the default. So what's that mean? Let's say that order system, it produces 100,000 messages. Order system 1, 2, 3, they produce, let's say, 100,000 messages in a minute, right? But on the payment side, we can handle only 20,000 messages in a minute. So what it means is we need to have a mechanism on the payment, on the downstream system side to handle as many messages as we can, right? So for example, on the payment side, if we want to only consume 100,000 messages, we want to consume only 20,000 messages in a minute, then we should be able to do that. So that's called the back pressure. So in this case is from payment, it's handled by default. So what does that mean? For example, in Kafka, right? It's handled by default. So payment system consumes as many messages as it can process. So for example, it consumes let's say that in a second it consumes 1,000 message or whatever the value that it can process. So it up to the downstream system to consume those messages and the process. So considering all this, what is the advantages of the event-driven architecture, right? There are a number of the advantages, but I marked in the yellow color those that I think is important to notice here. The first one is the loose complement, right? So what's that mean is that the producers they don't know about who the consumer event. So as far as that system is concerned, in our case, the order system, right? It produces the event, and on the downstream side, it can be consumed by one system or by many systems and so on. Another one is that, so one of the most important one is that it's asynchronous. So what's that mean is that the events are processed in the background without blocking. So from the producer side, again, as far as the producer is concerned, producers produce the event, and it's up to the downstream systems to consume those events and process them properly. Another one is the scalability. So each service or consumer can scale independently. So let's say that we want to consume more messages let's say we want to consume more messages on the payment system side, right? So we can scale that independently. So also it's extensible, which means that the new consumers can be added without changing the existing code. So it's resilient, which means that the failure in one system will not affect the others. Also, it's responsive, it's observable, and flexible, and so on. So these are the advantages of using the event-driven architecture. So now let's go to another example. Let's say that let's slowly go to the reactive programming. So we have an event-driven architecture, and let's say that the sub part of it, we can say that the sub part of the event-driven architecture is the reactive programming. So what I mean by that? So for example, in this case, let's say that we have an event and we are sending an event, and that event need to be processed. So again, asynchronously, right? That event needs to be saved to the database. That event needs to be logged, and so we need to send a notification about that event. So right, 3 different processes that should happen asynchronously, right? So we are sending an event, and that event should be asynchronously processed by these 3 systems. So again, one of the ways that we can do that is event-driven architecture, which means that we can place an event bus such as Kafka in the middle of it, and we can publish all our messages to Kafka, and on the downstream side, these services, right, saving to the database, logging a notification, can consume and process those messages. But What if we want to do that as a part of the one JVM? Let's say that we don't need to spin up a separate Kafka cluster. We don't need to spin up a separate Zookeeper and so on. We just need to, as a part of one JVM, as a part of one within the one JVM, as a part of one program, we want to consume message and save the message to the database log and send notification, and we want to do that asynchronously. That's where reactive programming comes into the picture in Java. So basically, it means that we are reacting to the event. So whenever we receive an event, we are processing that event asynchronously by considering the back pressure also. It's an important concept that I've mentioned earlier. Now that we know that what is the reactive programming, let's take a look at how reactive programming has evolved in Java. So let's start first with the pre-reactive era, right? Which is that before 2011. So before 2011, the way how we could create an asynchronous code, asynchronous program, or asynchronous or reactive program in Java is to use a feature. So feature has several disadvantages. One is that it has a callback issue, it has no unified abstraction, and that there is no back pressure handling in the future. And also feature can be blocking. For example, in this case, if we get our future, if they will try to get the value from our future, then in that case, this part of the code is blocking. So the next one is that was introduced around 2012 and 2013 is RxJava 1. RxJava 1 was introduced by Netflix as a counterpart to whatever already existed in the C#, observable pattern in the C#. So basically, observable pattern is another way to saying that the producer, right? I've already mentioned that we use either producer or publisher. Another way to say that we have a publisher is observable. So in this case, what we have is that we have observable that, for example, in this specific example, right, publishes 3 events, A, B, and C. And what we do is we are mapping those events to lowercase, and we have subscribers that basically subscribe and prints those events. So the biggest disadvantage of the RxJava 1 was that it wasn't handling the back pressure. So the next one is that around 2015, the way how we can create a reactive stream APIs, frameworks, libraries, and so on, it was streamlined, and 4 interfaces as a part of the reactive stream specification, 4 interfaces, publisher, subscriber, subscription, and the processor that I've mentioned here, they were introduced. These 4 interfaces are the backbone. They are the main foundation for the reactor, for the Akka streams, for the RxJava 2, and the Flow API that we are going to review a bit later. So the next one is in 2016, Rx1 was improved to the RxJava 2. Flowable was introduced in order to handle the back pressure. Again, the flowable is another way of saying of a publisher, but in this case, it was introduced in order to handle the back pressure in reactive streams. So the next one is that Java. So starting from the Java 9 in 2017, Flow API was introduced. It's a part of the JDK, so you don't have to include any library, any external framework in order to use the reactive streams in Java. So it's a part of the JDK. So now let's go and take a look one example of it. In here, I have an example for the stock price streams. So basically what we have here, right? So what we have here is we are creating one publisher and we are creating 2 subscribers. Again, we are using a flow in order to handle the back pressure. So what we do is we have 4 methods here that we are implementing, right? First one is the subscribe, on next, on error, and on complete. So basically we are telling our subscriber what to do when it just starts to subscribe, what to do when it's on the next, right? So here we are defining the back pressure, right? So we are defining how many items this specific subscriber should handle when it starts first, and then after that one by one. In this case, we are handling it one by one, but it could be like let's say that we can put here 2 or 3 or whatever value we want. But let's say how many events our subscriber can handle, right? So here what we have, so we are it's a stock price stream, so we are streaming a stock prices, and the first one is that we are displaying that we have 2 asynchronous jobs, right? Subscriber 1 displays those events, displays those prices for the stocks on the dashboard, and we have another subscriber which is that the log to the database. Right here we have exactly the same, so we have 2 subscribers. The first one is that showing that on the dashboard, and another one logging to the database. So here again we are implementing 4 methods, and we are defining that what should be for each case, right? For each case, what should we do? So whenever our subscriber starts, then we are consuming one event, one item, one event at the time, right? Then here, what we do is we are simulating some work, saving to the database, and again, we are consuming, as the next step, we are consuming again one event. So we are consuming event, as long as we have events, we are consuming events one by one, right? And on the error, we are throwing this message. We are returning to, so whenever we cannot handle the event, that's the error that we are throwing. And on the complete, we are logging again that the DB logger stream closed. And here, what we do, right? We have already created a publisher, and we have 2 subscribers. So we are registering our subscribers in our publisher. Again, if you have seen the observable design pattern, that's what exactly we do in the observable design pattern also. So here we are registering our subscribers, and we are starting the stock price stream, right? So here we just have we have a value for the stock prices. Let's say for the Apple, we have here some values, some random values here, and we are publishing those events. So we are one by one publishing those events to the so we are publishing those events, and we want to see that how they are subscribed by our subscribers, and we are simulating the live feed. We are publishing them every second. So then after we finalized all our work, we are closing the publisher in order to not waste the resources, and also we are printing this message, and we are keep the thread alive in order to print all the values. So that's it. That's all we have here. The important points to pay attention, again, we are using a flow, right? Flow interface here, and also that how we are handling a back pressure, right? Whenever our subscriber starts here, it processes one message, and on the next means that on the next message it again fetches from the list of the events, fetches one event at the time. So we can again increase that to 2 or 5. If we put here the value of the long maximum, it means that it will try to process all the messages at once. So now let's run it and see that it exactly works as we expect it to work. Let's run it. Okay, as you can see here, so we are starting a stock price stream, and we are receiving the event, and we are asynchronously, what we do, we are logging that to the database, and we are also showing that on the dashboard, right? Updating the dashboard. So we can publishing, we are saving to database, and we are showing updating the dashboard. So at the end, we are closing our publisher, so not to waste the resources, and our subscriber also exit because there is no event to process. So that's in a nutshell how Flow API works. So now let's go back to let's go back and see what we have, right? So again, a Flow API, it's you mainly used for the educational purposes, but if let's say you want to create the production level in the large project, usually we are using other frameworks and APIs that we are going to talk about now. So the next one is that the project Reactor, it was created around 2016. So basically project Reactor is a foundation for the Spring Web Flux. So it introduced two
entities. One of them is the mono and the flux. Mono is basically that we are emitting only one event at the time, right? So in the back, it's a back pressure aware, which means that it handles the back pressure out of the box. Next one is that the Spring Web Flux. It was introduced starting from the Spring 5, starting from the 2017. So basically, for the Spring Web Flux, so what we have here is that, for example, right here we have endpoint hello, and we are returning one event. We are using mono. As I said, mono means that we are just emitting one. We are sending one event. So here we are sending hello reactive world asynchronously. And the advantages of it is it's a non-blocking, it's built on top of the Reactor native, and it's great for the high concurrency APIs. So now let's take a look at we have seen all the options that we have. Now let's see that let's take a look one more view on the ecosystem of our reactive programming in Java. So language level API. Language level API, we are using Java 9 Flow. It's part of the JDK. So for the reactive libraries, we have a reactor, and we have the RxJava. We have RxJava 1, and we have RxJava 2 that was introduced by the Netflix. It's for the async pipelines, and the reactor is Spring Web Flux is based on the reactor. For the frameworks, we have a WebFlux, and we have also Akka. So for the reactive web, right? WebFlux is basically that we are using Flux for the web, right? Meaning that we are using that for the web applications. And for the large system, for distributed systems, let's say not part of the one. So if we have several downstream systems, and we need to better scaling, and we need to better management of our resources, then in that case we can use Kafka for the larger systems. And let's summarize and put some recommendation here. So we have as an APIs, we have a Future, we have RxJava 1 and 2, we have Flow API, we have a Reactor, and we have a WebFlux, right? So all of this except Future and the RxJava 1, all of them are handling the back pressure, and all of them are non-blocking, except Future. Again, Future, you should use that carefully because it can be blocking, as we have seen earlier. And usage of it, Future and the RxJava 1, they are usually used in the legacy applications, and Flow API for the educational purposes, and the Reactive WebFlux used in the reactive web or in the large applications. So the final recommendation is that if you are using a basic asynchronous calls, right? Basic asynchronous application you have, in that case, using a completable Future would be enough. But if the project is larger and you need much more ways how you can manage your resources, and how you can manage better control over your APIs, then in that case you should go with the Reactor and WebFlux. And for the distributed systems, you should go with the Kafka. To understand virtual thread, let's run this example. In this example, what we do is we are running 10,000 concurrent threads. First, we are running them using traditional thread pool, platform threads, and for the next one, we are using the new virtual threads project Loom that started from the Java 21. So let's run it and see that what it will give us. So in our example, what we do, right? In our example is very simple. In our example, we are just taking the benchmark from the start to the end, and we check that how long it took for 10,000 threads to run in the traditional. If we are using a traditional thread pool, or if we are using a virtual thread. And here what we do, so we are passing here executor, and we are passing here the number of the tasks, and we are putting the thread to sleep, we are here simulating the blocking IO operation, right? Let's say we are calling a DB, we are fetching some data from the database, or we are making an HTTP call, so we have some IO operation. So we are putting each thread to sleep for 1 second, and for each 1000 thread, we are printing the value. So we are printing the task ID and the thread ID just to take the benchmark, how long it took for the 1000 threads to complete, how long it took for the 2000, 3000, and so on. And at the end, when all the threads finish its work, then we are taking the how long it took, we are taking the benchmark, and we are printing that. Let's run this example and see that what it will show us. Let's run. It's gonna take a while, so I'm gonna pause here, and I'm going to proceed after all these threads complete its work. Both traditional threads and the virtual thread completed its work, and now we have numbers, we can compare them. So in this case, the first one, right, for the traditional threads, we are running 10,000, we run the 10,000 threads, and it took us 52 seconds to complete that work, right? It took us 52 seconds. And if we compare exactly the same with the virtual thread, it took us only 1 second to complete. So it's a 50 time faster than the traditional threads. But now let's go understand that where exactly that comes from, right? So in our case, we did one thing. Our scenario is in our scenario, for each thread, we have a blocking call. We have a blocking IO call. We are simulating the call here. Either we are calling a DB or HTTP call, and so on. Let's understand where that advantage comes from, right? First, let's understand what is the Project Loom. Project Loom was introduced as a part of the Java 21. So Project Loom is basically a long-term open JDK effort to simplify the concurrency. So it introduced two main features. The first one is virtual threads that we are reviewing right now, and then in our next episode we are going to review also the structured concurrency. What is the Project Loom, right? What is its advantage? Think of it as Java's answer to the async await or the coroutines or the similar multithreading efforts in other languages. So what is in our case, right? What is the virtual thread? Virtual thread, basically it's a lightweight thread managed by the JVM. But to go there, to understand that what exactly it means that it's run by the JVM, let's first understand how our traditional platform threads, how they exactly work. The way they work, so when we are creating a thread in Java, the way it works is that that thread is managed by the OS scheduler. So we create a thread, and the OS scheduler maps that thread one-to-one to the operating system thread, right? It's expensive because for each thread we are creating 1 megabyte. We are creating a separate stack, which is 1 megabyte, right? It's hard to scale beyond a few thousand threads at the time. And it's also for the blocking operations, the thread blocks itself, right? So we have one-to-one mapping. If we create a thread in a traditional platform threads, then it's a one-to-one mapping to the operation system threads. But what happened in case of the virtual thread? In the case of the virtual thread, we still have those threads, right? We still have those threads, but we are calling them carrier threads, and the carrier threads are still one-to-one map, one-to-one to our operating system thread. But on the JVM side, what we do is we are creating the virtual threads. All the threads that we have seen here, all the threads that we have started here, these threads are basically in case of the virtual thread, right? All these threads, new virtual thread per task executor, all these threads are virtual threads, and we can create as many virtual threads as we want for one one carrier thread, right? I hope it's clear. So basically, we still create one-to-one mapping from the, if we create a, we still create a carrier thread, which one-to-one map to the operating system thread, but on the background for one carrier thread, we can create countless number of the virtual threads. So basically, if to summarize, we have each carrier thread is still, we are creating, it's a one-to-one mapping for the OS thread, and the virtual threads are parked and resumed by a JVM. So the reason why it was much faster earlier, because whenever we have input-output, whenever we have input-output operation, whenever we have a blocking call, in that case, JVM parks that virtual thread, and resumes that thread when that thread finalizes its work, right? So JVM handles the scheduling, not the operating system. It's virtual threads, they are ideal only for the IO-bound concurrency, which means that whenever we are making a call, whenever we are making external call, and whenever our thread is idle, then in that case, we can leverage the advantage of the virtual threads. Otherwise, let's say that if our application is the CPU bound, we need the more CPU power, then in that case, virtual thread don't have that much advantage. So, but how exactly virtual thread is parked and resumed, right? Let's take a very simple example. Let's say that the virtual thread start executing a user code, right? So what happens is that the virtual thread, let's say 42, it mounted on the carrier thread. So basically it mounted on the thread which is running on which is one-to-one mapping to our OS thread, right? So it executes user code and it's running on the CPU, and the step 2 is virtual thread hits the blocking call, for example, thread sleep, or let's say that the call to the external system, or some blocking operation, right? So in that case, what happens is that the virtual thread 42, in our case, right, JVM intercepts that, JVM saves that stack frame on the heap. So in our case, we are in the traditional multi-threading. For each thread, we are allocating 1 megabyte memory, right? In this case, we don't do that. We save the stack. We take the stack frames on the heap, which takes only few kilobyte. So now that the carrier thread 1 is freed now, so because JVM intercepted and freed that, and now we can perform other operations, right? So carrier thread returns to the JVM scheduler. So, and as a step 3, carrier thread picks another runnable virtual thread and runs it. So in our case, the reason why it was fast again, because all those seconds that the thread was idle, carrier thread was idle, it was running another thread, right? It was running another thread, while for the traditional multi-threading, we have to wait for that thread to finish its work. So then now it's carrier thread picks up another virtual thread. Let's say it picks up virtual thread 87, and now let's say that our previous one, 47, right? Let's say virtual thread 47 completes its work, and or let's say that the sleep time expires. So what happens is that the JVM scheduler remounts the virtual thread 42 to another carrier thread, right? It could be the same carrier thread, it could be different, and the virtual thread 42 resume its work. So that's basically it. So again, when we are starting a virtual thread, carrier starts it. When it hits the IO bound operation, let's say that there is some blocking calls, then in that case it's the state of that thread, virtual thread, saved on the heap. We are parking it, and once it's finalized its work, another carrier picks that thread from the heap and continues its work. So as a result, what we have is our OS thread or a carrier thread is never idle, waiting for the IO operation to complete, or we don't have any blocking calls. And if we do that, which means that the virtual threads can be scaled to the millions of threads very easily. So if we compare I put here some comparison summaries. So if we compare feature and the feature for the platform and the virtual thread, so they are backed by platform thread is backed by OS thread, which means that the OS scheduler, but the virtual thread are managed by the JVM scheduler. For the stack memory, again, in case of the platform thread, we need to, for each thread, allocate 1 megabyte. We are creating a separate stack for each thread, and we need to create 1 megabyte. We need to allocate 1 megabyte memory for each. For the virtual thread, it's just a few kilobytes on the heap. So for the blocking behavior, it blocks the OS thread, and in case of the virtual thread, it parks and frees the carrier. So for the scheduling, it's again scheduled by the OS, and here it's scheduled by the JVM. And for the scalability, it can go as high as thousands, but in case of the virtual thread, it can go to the millions. It's a platform threads. They are best for the CPU bound, and for the virtual thread, as we have seen earlier, they are best for if we have a lot of I/O operations, making HTTP calls and similar, making them connecting to that database. So then virtual threads are ideal for those cases. So key takeaways that Project Loom makes high concurrency simple and natural. Virtual threads are still real Java threads, just cheaper. JVM handles parking and resuming, freeing the operating system for more work. And the many virtual threads, few carrier threads, and we may have here millions of the virtual threads. For those threads, we may have only, let's say, 5,000 of the carrier threads, which are mapping exactly to the operating system threads. So when to use it, when to use the virtual threads, and when to not to use them, and use the traditional threads. As I mentioned earlier, they are best for the intense I/O or I/O apps. When we have intense I/O in our application, for example, network call, DB call, or HTTP call, then in that case we should use the virtual threads. And when we should avoid to use them, we should avoid to use them if our app is doing the CPU bound task, which means that the image and video processing, compression and decompression, and the similar heavy CPU bound operations. Let's take a look at another feature of the Loom project, which is the structured concurrency. And let's take this very simple example. Let's say that we want to fetch a user, we want to fetch a user data, and here we're printing whatever we fetch. In our fetch user data, what we do is we are creating a scope, and we are creating a structured task scope. And in our scope, we are dividing our task to two parts. Let's say that we are fetching them from the different databases or from the different HTTP endpoints. So we get the user and we get the email separately, right? After that, what we do is, if the both tasks are complete, then we are joining. If not, then in that case, we are throwing an exception. And at the end, we are combining and returning the result. But what happens in the background, right? So what happens is under the hood. So we have a parent scope, a structured task scope, which divides our tasks that we are creating here, right? Which divides them into different virtual threads. So we are running them in different virtual threads, in each one in the separate thread, and we are waiting for them to complete. Parent, in this case, the parent scope is waiting until all tasks finish or one task fails. So let's say that in this case, let's run it. In our case, both of them complete successfully, so we are combining the result, John Doe, and we are returning the result, right? But what happens if in one of these cases we get the exception, right? We get some error. In that case, in our case the whole result will fail, because we are either succeeding, so either waits until all of the tasks complete, or it waits until one of the tasks fail and returns the result.